All right. Well, it is my pleasure to introduce Rajesh Pereira, who will give our colloquium today, our hybrid colloquium. He will speak about approaches to the doubly stochastic spectral region problem. Rajesh, take it away.
Oh, thank you very much, and I'd like to thank the organizers for inviting me to the seminar series. So let's first kind of discuss sort of basic definitions. So a square matrix is called stochastic if it's entry-wise non-negative and all of its columns sum to 1. If, in addition, its rows also sum to 1, then it's called a doubly stochastic matrix. And so stochastic matrices have all sorts of applications, and they're very interesting. And one of the things people are interested in is what could be the eigenvalue of an n by n stochastic matrix. So in 1949, Karpilevich gave a characterization of the set of all complex numbers, which can be the eigenvalue of an n by n stochastic matrix. This region is complicated to describe, but it's not the entire unit disk in the complex plane, or for that matter, even convex. It intersects the unit circle only at the kth roots of unity, where k is less than or equal to n. I'm not that good at computer software, but my former PhD student who was kind of involved with the research in this area is. So, whoops, let me, yeah, I think I did it correctly. So let me actually switch to his PhD thesis. So this, could you see the diagram that I have on so am I still sharing?
Yeah, it looks good. We can see
Perfect.
curvy
So
non-convex region.
yeah, so this thing, which kind of looks a little bit like a manta ray. So the region is this filled in area here. This is the region of all eigenvalues of 4x4 stochastic matrices. And so it is, and the as the number gets higher, 5x5, 6x6, the region gets larger and larger. And eventually the union of all of these regions is, in fact, the entire unit disk, but we never actually get to the unit disk for any finite n. Now, if we replace stochastic by doubly stochastic in this, actually things change by quite a lot. So what about the set of all complex numbers, which can be the eigenvalue of an n by n doubly stochastic matrix? Now, this region, if we sort of graph it numerically, it actually seems to be a lot simpler than the stochastic case. The stochastic case has all sorts of weird curves, and the doubly stochastic case is actually seems quite a bit simpler, but it's harder to actually solve the problem. So the first people who looked at this were Hazel Perfect and Leon Mirsky in 1965. And so let pi sub k be the k-gon in the complex plane formed by taking the convex hull of all kth roots of unity. So if we take the convex hull of all kth roots of unity, and now we get a regular k-gon. And they conjecture that the set of all possible eigenvalues of n by n doubly stochastic matrices is the union, k going from 1 to n, of these k-gons. And this is how they wrote this conjecture. But it's actually fairly easy to see that any pi sub k is strictly contained in pi sub 2k. So there's a bunch of redundant ones in there. So it's really k goes from the ceiling of n over 2 to n, the union of those k-gons. And it's actually not too hard to show that anything in this set, which I'm going to call the Perfect-Mirsky set, is in fact the eigenvalue of an n by n doubly stochastic matrix. And for those of you who know circulant matrices, which I'm not going to define, if you take direct sums of n by n doubly stochastic circulant matrices, that is enough to get you this entire set. And so this is their conjecture. And this is actually the progress that's made on the conjecture. We haven't actually gotten that much. The Perfect-Mirsky conjecture is true for n equals 2 and n equals 3. That was actually solved by Perfect and Mirsky in their paper. In 2014, a group of us at the University of Guelph, including the student whose thesis you saw a little bit about, we were actually able to show that this conjecture is true for n equals 4. But it was actually shown by two mathematicians at Laval University in Quebec City, that for n equals 5, this conjecture is actually false. So they came up with a numeric example of a 5 by 5 doubly stochastic matrix whose eigenvalue lies outside that Perfect-Mirsky region. But kind of interestingly enough, it doesn't lie that far outside. So it's very close to the Perfect-Mirsky region. So the Perfect-Mirsky conjecture, even if it's false, it's probably not false. Well, we know it's false, at least for n equals 5. It's probably not false for, it's probably approximately true. So in fact, much of the recent progress is actually, in this problem has actually been done in Canada. Now it's open for n greater than or equal to 6, but a lot of people actually think it's true based on the numerical evidence. Although I must admit, I'm actually one who's not convinced by this, mainly because I suspect that there's a possibility that we could get something similar where you get something that's outside, but not too far outside. But we actually don't know. So that's just sort of a pure guess on my part. So how do we solve this? Well, for the stochastic matrix case, Karpilevich solved things. So kind of the obvious thing to do is to take a look and see how did Karpilevich solve his solve this problem for stochastic matrices. And he didn't phrase it this way, but he was actually considering essentially a partial order on the set of complex numbers. So suppose, or I should say on the set of complex vectors. So suppose I have two vectors, A and B. I'm now going to define a partial order on the complex n vectors, where A is less than or equal to B, if the convex hull of the elements of A are contained in the convex hull of the elements of B. So that's my that's my partial order. It's fairly easy to see that this is a partial order. This actually has a matrix theoretic interpretation. So let V and W be n vectors. Then V is less than or equal to W in this order if and only if there exists a stochastic matrix S such that V is equal to S transpose W. And essentially what Karpilevich was doing was his proof kind of gives a way of keeping track of when a complex number could essentially, when multiplying the elements of a vector, when it sort of brings those elements into itself. So he's essentially using this partial order, at least implicitly. And now we could actually do something in the following. So suppose I have any partial order on the n vectors. Then lambda, lambda is not lambda is not in Cn. It's not a vector. It's a complex number. So lambda should be in C. This is called an eigenvalue of this partial order if there exists a non-zero V, a non-zero vector V, such that lambda V is less than or equal to V. We label the set of all eigenvalues of this partial order, defined that way, as the spectrum of this partial order. And now on Cn, the spectrum of this convex hull inclusion order is actually the set of all possible eigenvalues of n by n stochastic matrices. And the reason why this is actually kind of an important observation is, so there's actually not that much done with convex hull inclusion, but there is a corresponding order to the doubly stochastic matrices, which is actually extremely useful. And that's actually what I'm going to talk about next. So suppose I have two so here I'm taking two n vectors, but these are real n vectors. So the x vector and the y vector, we say that the x vector is majorized by the y vectors if, so the arrows here mean reordered in descending order. So if the sum of the kth largest xj's is less than or equal to the sum of the kth largest yj's for all k. And if the sum of all of the x's is equal to the sum of all of the y's. Let me actually give an example. To kind of understand this example, majorization was sort of invented in two different fields pretty much at the same time. It was invented by mathematicians for reasons I'm going to go into a little bit later, but it was also simultaneously invented by economists. The key economist was Lorenz, so economists call majorization the Lorenz order. And they actually use it to study income distribution. So majorization, essentially what it's what it's used for in economics, or one of the things it's used for in economics, is to compare income distributions. So as an example, the vector 2, 2, 2 is majorized by 3, 2, 1, which is itself majorized by 4, 2, 0, which is majorized by 6, 0, 0. On the extreme left, we have the most equal distribution, and on the extreme right, we have the most unequal distribution. However, this is a partial order, it's not a total order. So as an example, take the vector 4, 1, 1 and 3, 3, 0. They both sum up to 6, so there's the same total amount in each, but they're incomparable with respect to the majorization order. And the interpretation is kind of, so which is more equal? Well, it's hard to say, because at least with 4, 1, 1, everyone gets something. But on the other hand, 3, 3, 0, the top guy doesn't have as much, and the top two are equal. So it's actually hard to argue which is more equal. Whereas on the top example, everyone could agree between any two of those, which is a more equal distribution than the other. Now, one of the reasons, so this is kind of why economists are interested in it. So why are mathematicians interested in it? Well, the key thing for mathematicians is there are a lot of equivalences to majorization, which is sort of the major hint in mathematics that something is important. So for instance, compactness, there is an example of this. So for majorization, here are a couple of characterizations of majorization. So let I be any interval on the real line, and let A and B be n tuples of real numbers in I. Then the following are equivalent. So one, the A's are majorized by the B's. Two, the sum of a convex function of the AIs is less than or equal to the sum of that same convex function of the BIs. And that's true no matter what convex function I pick. Now, all discrete LP norms are basically of this form. So majorization is actually a way of getting LP inequalities. There exists a doubly stochastic matrix S such that A is equal to S times B. And this is the reason we find, this is the reason why this concept is interesting for what we're doing. Four, A is in the convex hull of all permutations of the B vector. And that's actually the equivalence of 3 and 4 is due to a result called Birkhoff's theorem, which I'm not going to go into. Now 5, I'm going to explain a little bit more in a little later. So I will tell you what a quantum channel is, but I'll sort of defer that. So there exists a unital quantum channel and a Hermitian matrix B, such that the eigenvalues of B are B, and the eigenvalues of lambda, the eigenvalues of phi of B are A. That the existence of this quantum channel is essentially equivalent to majorization. So majorization has become fairly important in quantum information. Largely, although not completely, because of this result. Now, the original sort of definition of majorization uses inequalities. So as a result, we can't really generalize these to complex vectors. And in fact, we can't generalize these to sort of tuples of real vector spaces with the original definition. But you'll notice some of the equivalent conditions could generalize quite nicely. In fact, both 3 and 4, which are essentially equivalent, those generalize in a pretty straightforward manner. So we could sort of generalize that. So one other thing I should say about majorization is there are actually people, majorization is part of the research of some people at Western, who one of whom does work in inequalities, and sort of 2 is kind of the connection into that, and another who is doing work in optimization. So it really does show up all over the place. So now we'd like to generalize this away from real numbers, and one way is to take the doubly stochastic matrix characterization and just run with that. So now let V be a real vector space, and let A and B be n tuples of elements of V. Then we say that A is multivariately majorized by B if there exists a doubly stochastic matrix S such that A is equal to S times B. So that's a very straightforward generalization of majorization, but it's not the only one. In fact, this has actually become a cottage industry. I don't have time to go into all of the generalizations of majorization, but they're actually really interesting. Another one that's going to show up and that's kind of useful in our in our work is what's called directional majorization. So let V be a real vector space, and let A and B be those n tuples of elements of V. Then we say that A is directionally majorized by B if the vector, the real vector formed of the f of A's, is majorized by the real vector of f of B's for all unit norm linear functionals f in V star. And this is also another way of generalizing majorization. If V is just the real numbers, both reduce to ordinary majorization. It's actually not too hard to show. Well, actually, let me, before I say that, let me actually mention that for our purposes, for the problem that we're considering, we'll always take our vector space to be the complex numbers. So that we're taking these complex numbers to be a 2-dimensional real vector space. And in this case, a unit length linear functional, so just of the form f of z is equal to the real part of e to the I theta times z. So that's actually what we're kind of doing for when we define directional majorization for complex vectors. So we could define directional majorization, we could define multivariate majorization. And the question is, are they the same? Well, one observation is if A is multivariate majorized by B, then A is directionally majorized by B. That's just simple algebra using the fact that linear functionals are linear. So that actually carries through in a completely nice way. But it actually turns out that the converse is false, even if we just restrict ourselves to the complex numbers. And this is an example due to Martinez, Massey, and Silvestre. So if we take A to be the fourth roots of unity, and if we take B to be the cube roots of 8, together with 0, so we add that in, then you could show that A is directionally majorized by B, but A is not multivariately majorized by B. And there are actually all sorts of examples like this. So directional majorization is a strictly weaker condition to be satisfied. You'll basically notice that for B is kind of interesting in the sense that if we plot the points in B, we've actually, the 0 lies in the convex hull of the other points. And that actually is a fairly key thing. And in a way, that kind of, in a way of thinking about it is 0 sort of gets hidden a little bit from the linear functionals. And the fact that 0 is in the convex hull kind of confuses the linear functionals in a sort of way. And we could see this in the following result. So this is a result by Bandari. In fact, it's older. So let A and B be complex n vectors, and suppose all of the elements of B lie on the boundary of the convex hull of the elements of B. So when we form the convex hull of the elements of B, all of the elements of B lie on the boundary, none are in the interior. And then a multivariate majorization and directional majorization are exactly the same. Now, in particular, if n is 3 or smaller, then this is always satisfied. Well, except for a straight line. So if the points are not, but even that, it's sort of on the boundary of the convex hull. So for n equals 3, the elements B form a triangle. And so this is actually always satisfied. So n equals 4 is the first case where directional majorization and multivariate majorization are actually different. And so this is just kind of direct from the definition of what multivariate majorization is. So if we're considering our partial order to be multivariate majorization, well, in the spectrum of multivariate majorization is the set of all possible eigenvalues of an n by n doubly stochastic matrix. So considering that the spectrum of this particular partial order is exactly what we want to find. It's exactly what Perfect and Mirsky are essentially asking for. But we also have this other partial order, the directional majorization. And it's clear that the spectrum of directional majorization contains the spectrum of multivariate majorization. That has to do with the fact that whenever you have multivariate majorization between two vectors, you automatically have directional majorization. Now, do we have equality? Well, yes, we do for n less than or equal to 4. For n equals 2 and n equals 3, this follows immediately from Bandari, his result. And we actually proved the n equals 4 case of Perfect-Mirsky by showing that in n equals 4, the spectrum of directional majorization is exactly the Perfect-Mirsky region. So it's exactly the convex hull of the cube roots of unity union with the convex hull of the fourth roots of unity. And because it's that, and because the spectrum of the multivariate majorization is contained in that, and because we know that the spectrum has to contain the Perfect-Mirsky region, this actually proves that the spectrum of multivariate majorization is equal to the Perfect-Mirsky region. But we actually did this indirectly. So in this case, the spectrum of directional majorization is easier to work with than the spectrum of multivariate majorization. Because the spectrum of multivariate majorization, essentially, it's just this conjecture. It's just rephrasing the conjecture. It doesn't really help us. Directional majorization, on the other hand, is actually nicer and easier to work with. However, with that being said, our result really does use n equals 4. So generalizing it will require some new ideas. But this is sort of a key question. What about the spectrum of directional majorization when n is greater than or equal to 5? Now, this wouldn't solve the original Perfect-Mirsky problem. It wouldn't solve the doubly stochastic matrix problem unless we're lucky and this spectrum is in fact the Perfect-Mirsky region, which of course it can't for n equals 5, because we know that's impossible, but there's still a possibility that it could be true for n greater than or equal to 6. And whenever the spectrum of directional majorization is equal to the Perfect-Mirsky region for any n, then the Perfect-Mirsky conjecture is true for that value of n. So this is actually a very interesting question. It's kind of the first open question I'd like to throw. Well, other than, of course, I guess there's the Perfect-Mirsky conjecture for n greater than or equal to 6. But this is actually a very kind of interesting question that I'd like to throw out there. Now, another conjecture, and this is actually the first time I'm stating this conjecture. So a point. So first, a definition. So a point A in S of a real vector space V is said to be a star center, and I should say a star center of S. I don't have that written up. So it's said to be a star center of S if for every X in S, the line segment joining A to X also lies in S. So a set which has a non-empty star center is said to be star-shaped. The set of all star centers of S is called the kernel of S. And this is denoted as kernel of S. And both the so both the doubly stochastic region, it's fairly easy to see that that's star-shaped. And in fact, it's a fairly easy exercise in linear algebra to show that any number between 0 and 1 lies in the star center. And the same is actually true of the Karpilevich region. So the Karpilevich region is also star-shaped, and any element between 0 and 1 must lie in the star center. It's somewhat harder to prove that other numbers line the star center, but they do. So one observation, completely general about the kernel of S is the intersection of all maximal convex subsets of S. And now we have the following conjecture. The kernel of the set of all possible eigenvalues of n by n doubly stochastic matrices is the intersection of these n-gons. So the n-gons going from where, or sorry, the k-gons. So the k-gons of the convex hulls of the roots of the kth roots of unity, the intersection where k goes from the ceiling of n over 2 to n. Now, if the Perfect-Mirsky conjecture were true, then this conjecture would automatically follows from the Perfect-Mirsky conjecture. Now we know the Perfect-Mirsky conjecture is false, but it's fairly easy to see that the little bits that kind of move outside the Perfect-Mirsky region aren't actually going to affect the kernel. So this conjecture is almost certainly true. So of the things in mathematics that I can't prove, I'm actually the most confident about this particular conjecture. It's almost certain that this is true, but it's still a pretty it's still a pretty hard thing to try to prove, even in the small cases. Although it is true for n up to 4, because the Perfect-Mirsky conjecture is true, and this follows immediately from the truth of the Perfect-Mirsky conjecture. So this is sort of another conjecture. Now you might be thinking, okay, this stuff might be interesting to matrix theorists, but what about other mathematicians? Well, I think it should be interesting to other mathematicians as well, because there actually is a fair bit of group theory attached to this. And to kind of see how group theory connects up with this, what we're going to do is we're going to come up with yet another generalization of majorization. Now, remember, one of the equivalent conditions for majorization is A is majorized by B if the vector A lies in the convex hull of all permutations of B. And this conjecture, sorry, not this conjecture, this characterization of majorization, it also remains true whenever A and B are not just real numbers, but lie in a real vector space. So for instance, if they're complex numbers, this characterization is now a characterization of multivariate majorization. But now, suppose instead of asking for it to lie in the convex hull of, instead of asking for it to lie in the convex hull of all of the permutations of B, we ask it to lie in the convex hull of some subgroup of the permutations of B. Then we actually get something called G-Majorization. And if G is a cyclic subgroup, it's called cyclic majorization. And cyclic majorization is actually sort of interesting enough that it's studied by statisticians. And in fact, G-majorization in general, a lot of the research is actually from statistics. And well, we talked a little bit about the spectrum of these partial orders, and other than the n equals 4 case, I'm listing a lot of problems, but no solutions. Now, if G is nice, it's actually not too hard to calculate the spectrum of these. It's actually not too hard to calculate the spectrum of the G-majorization. So if G is cyclic and generated by a permutation containing cycles of length C1, C2, and CR, then the spectrum of G-majorization, this is equal to the union of pi of the C's. And this is kind of interesting because this looks a little bit like the Perfect-Mirsky region. And so the question now is, when is the spectrum of G-majorization a union of regular polygons with roots of unity as vertices? Now, the answer is yes for G abelian, and that follows from that previous result. So it's kind of clear for G being cyclic, but it's a little bit more complicated for G being abelian to state, but it's relatively straightforward. It follows from using the theory of characters. The only non-abelian cases we know for are essentially the Perfect-Mirsky, the cases where we know for Perfect-Mirsky. So G is equal to S3, G is equal to S4. The answer is yes, because the Perfect-Mirsky conjecture is true. And it's no for G is equal to S5, because the Perfect-Mirsky conjecture is false. Now we can ask an even more specific question than this. When is the spectrum of G equal to the spectrum of G-majorization? When is it equal to the union of the spectrum of H-majorization, where where the union is taken over all H's that are cyclic subgroups of G? And the answer is exactly the same for this more specific question than it is for the question above. Yes, if G is abelian, when G is equal to S3, G is equal to S4, and no when G is equal to S5. This particular more specific question is actually equivalent to the Perfect-Mirsky region, the Perfect-Mirsky conjecture when G is a symmetric group. So this particular question can be viewed as a generalization of the Perfect-Mirsky conjecture. And yeah, so that's actually kind of what I said here. Both of these, when G is the symmetric group, both of these questions are equivalent to the Perfect-Mirsky conjecture of order n. And so now you might be asking, okay, why does S5 not work? And solvability was actually an early conjecture, because all of the, at least for what we know, all of the groups which work are solvable. The one group that doesn't happens to be the first group that we encountered, which was not solvable. And this may still be true, but the fact that people think that this is true for S6, S7 means at least one direction of this is probably not true, unless I'm right and it fails for higher dimensions as well. Now, there's a connection with group representations. So the n by n permutation matrices, they're a representation of Sn, but not an irreducible one. Because if we take the permutation matrices, the span of the all ones vector and its orthogonal complement, those are both invariant subspaces of the permutation matrix. And the permutation matrices are therefore, it's fairly easy to see that this is the direct sum of the trivial representation and another representation, which is a hook representation of the symmetric group. And it's the latter which contributes the non-trivial eigenvalues, because the all ones vector always just gives us the eigenvalue 1. So this motivates probably the ultimate generalization of this question. So let G be a finite group, and suppose I have an irreducible representation of G. And so now if we take this irreducible representation and each group element corresponds to a unitary. Now let C be the convex hull of these unitaries. So call the set of all eigenvalues of elements of C the spectral region of this representation. So what can we say about the spectral regions? When are they the unions of regular polygons with vertices on the unit circle? And because the representations are all characters, which are 1-by-1 matrices, it's very easy to calculate when G is abelian. And of course, it's clearly true. For the hook representation, this is again equivalent to the Perfect-Mirsky. So I think I have 2 slides left. So I want to talk a little bit about the quantum version, simply because, as I was talking about a little bit earlier, quantum theory is pretty big, and it's a lot of the research that I'm doing now. So a probability vector is a non-negative vector whose entries sum to 1, and a matrix is stochastic if and only if it preserves the set of probability vectors. The quantum analog of probability vectors are the density matrices, positive definite matrices with trace 1. And a linear map is said to be a quantum channel if, well, it's a bit stronger than it preserves the density matrices, but if I tensor it with any k by k identity, that resulting map preserves the nk by nk density matrices for all k. And that's the definition of a quantum channel. So in a sense, a quantum channel sort of generalizes a stochastic matrix. Now, the set of all complex numbers, which are an eigenvalue of some quantum channel, even in the smallest dimension, in the 2-by-2, a quantum channel in the 2-by-2 matrices, this is the entire closed unit disk in the complex plane. And I give a hint as to how you could show that. So if we're talking about the set of all eigenvalues of all n by n quantum channels, that's very uninteresting. It's the entire unit disk. Now we could restrict the quantum channels a little bit. So we consider the entanglement breaking channels only. So of course this definition, unless you're familiar with what being separable is, this definition is not going to make that much sense. But so basically what an entanglement breaking channel does is, if we take the entanglement breaking channel, tensor the identity, any entanglement of that, it will break, which is kind of So these are interesting for reasons. Now, if we restrict ourselves to just entanglement breaking channels and say, what is the set of all possible eigenvalues of entanglement breaking channels? Well, and so this is a very recent result. So the three authors of the original n equals 4 case plus two others. So we were able to show that the set of all complex numbers which are an eigenvalue of some entanglement breaking channel on the n by n matrices. So from the n by n matrices to the n by n matrices, this contains the order n Karpilevich region and is contained in the n squared Karpilevich region. Now we haven't characterized it because it's really kind of a horrible thing, but it is interesting and it is sort of connected with with kind of these Karpilevich regions in ways that we don't quite understand yet. And that's where I want to end. So thank you very much.